In this video, I will go over Maxwell's equations, and I will remind you all the material that we've covered, and I will also review when we use each one of the four equations and how they can be helpful. So the first one, we have Gauss's law for electricity. The divergence of the electric field is the charge density over epsilon naught. This is the differential form of Gauss's law. Now, what can we find from this one? If you know the electric field, okay, if the electric field is given, if you know it, you can find the divergence of it, and that will give you the charge density. Now, if we express Gauss's law in the integral form, I have the closed surface integral of E dot dA is equal to the charge enclosed over epsilon naught. Now, the integral form of Gauss's law, we can use it if you know the electric field again, you can find the charge enclosed. However, if you have the charge enclosed and you have symmetry, then this allows you to find the electric field. If you remember, we've used Gauss's law in the integral form in cases where symmetry allowed us to pull out the magnitude of the electric field out of the integral, and we were able to use the charge and the given charge enclosed to find the electric field. So from Gauss's law, we can find, okay, if you want, you can find the charge density, you can find the charge enclosed, or you can find the electric field if you have symmetry. It is important, I do want to mention that Gauss's law is always valid. Okay, we've talked about that. Gauss's law is always valid, but it's not always useful. If you want to find the electric field using Gauss's law, you have to have symmetry. Okay, you cannot find the electric field using Gauss's law if your problem, if your situation does not include symmetry. Okay, and that's what we did. Every time we had spherical, cylindrical symmetry, we were able to take the magnitude of the electric field out of the integral and then solve for E. So remember, Gauss's law, always valid, not always useful. Now, I do want to mention, the first thing that we did in electricity is Coulomb's law. Okay, but of course you don't see anything similar to Coulomb's law here in the for Maxwell's equations. Actually, Coulomb's law can be derived from Gauss's law. So if you assume that you have a single point charge and you use let's say at the origin, and you use a spherical cell for your Gaussian surface here, you will find that the electric field is given by Coulomb's law. So remember that Gauss's law includes, in a way, Coulomb's law. And of course, Coulomb's law for a single point charge, if you follow the process that I've talked in the past, where if you have a charge distribution, you divide it into small pieces, you choose an arbitrary piece, and then you find the contribution to the electric field from that small arbitrary charge, part of the distribution. Then you add up all the contributions to the electric field from that small from the individual pieces, and then you convert your sum into an integral. You can find the electric field using Coulomb's law from charge distribution. So all of that is included in Gauss's law. Now, I also want to mention, when the curl of the electric field is 0, we said that we will define the electric potential as minus the gradient. The electric field is equal to minus the gradient of the electric potential. And if I use this expression in the differential form of Gauss's law, then I get that the Laplacian of the potential, and here I need to erase there is no line in the Laplacian. The Laplacian of the potential is equal to minus the charge density over epsilon naught. Now I want to, so the way that I obtained the Laplacian is by using Gauss's law in the differential form, and I plugged in minus the gradient of the potential. You get a Laplacian. If you have an area where the charge density is 0, then the Laplacian becomes equal to 0. The Laplacian of the potential is equal to 0. And I want to remind you, this is Poisson's equation. Okay, and we used Poisson's equation and the method of separation of variables along with the boundary conditions to find the potential in an area. Now, all of these that I talked about is included in Gauss's law. Okay, so when you encounter Gauss's law, remember it's always valid, not always useful. You can find the charge density, you can find the charge enclosed. If you have symmetry, you can find the electric field from the integral form of Gauss's law. And if we make the assumption that the curl of E is 0, then you obtain Laplace's equation. If your charge density is 0, you obtain Poisson's equation, and from there you can move on with the techniques we learned to find the potential. And of course, if you have the potential, then you can go back and find the electric field. Now, all of this, and Coulomb's law, I forgot to mention. Gauss's law includes Coulomb's law. An interesting fact, Coulomb's law is not relativistically correct. Okay, you can use Coulomb's law if your charges are not moving, but interestingly, the Gauss's law is actually relativistically correct. So this equation is valid if your charge is moving at very high speeds compared to the speed of light, but Coulomb's law will not work when your charge is moving too fast. All right, now the next one we have Gauss's law for magnetism. The divergence of B is 0, and that really is not telling us many useful things. So the right side is 0. The integral form, you can express it as the closed surface integral of B dot dA is 0. How can you use it? The only thing you can do with it is if you are given some patterns, some vector fields. What you can do with Gauss's law for magnetism, you can discard some vector fields as being physically unreasonable, physically wrong, because they don't obey Gauss's law for magnetism. But other than that, you cannot really obtain anything else, and that's why we have not done much with it. Now, the next one, the next Maxwell's equation is Faraday's law. And of course, this is very, very interesting and a very useful physics principle. In the differential form, the curl of E is related to the time derivative of the magnetic field. In more simple words, if your magnetic field is changing, then you know that at the same time you have an electric field, and you have an electric field that is actually a curling electric field. The curl of E would not be 0. if your magnetic field is changing. Now this is Faraday's law, and we have used it a lot in the integral form. The closed path integral of that non-Coulomb electric field dot dl is equal to minus the derivative of the magnetic flux, and we have seen we calculate the magnetic flux as the surface integral of B dot dA. Now, how have we used this in the past? If in cases where we know how the magnetic field and the flux is changing, we have been able to find the induced EMF, and we have also been able to find the strength of the non-Coulomb electric field. This is primarily how we use Faraday's law. This is we know that there is a changing magnetic field, and we use that to find the induced EMF, the induced electric field, and if you have a circuit there, a loop with a resistance and so on, you can find the induced current. This is the primary way that we use Faraday's law in situations to find the induced EMF and the induced current in the circuit. Now, the next one is I can make some notes. So from here, what we can get from it, the induced EMF and also the induced current, and sometimes the non-Coulomb electric field that comes at whenever you have a magnetic field that is changing. Now, for Gauss's law in magnetism, as I said, we can use it to sometimes find the physically unreasonable magnetic field patterns. All right, and finally we have the Ampere-Maxwell law, the Ampere-Maxwell equation. We have in this expression, the curl of the magnetic field and the time dependence of the electric field are related. Here, this expression shows us that the current density is what gives rise to a magnetic field and perhaps a time-changing electric field. Now, the way that we've used Ampere-Maxwell's law when the electric field is not changing with respect to time, and this quantity goes to zero, then we have done B dot dl is equal to mu naught times the current enclosed. Now, what did we get from that? This is similar to how we used Gauss in a way how we used Gauss's law in electricity. You can find. So here I am assuming that the time derivative of E is 0. Here you can find, if you have B, you can find the current that you have enclosed by your path integral. If you have symmetry, you can also find the magnetic field, if symmetry allows you. And if your problem does have symmetry, Ampere's law, where the time derivative of E is 0, is by far the easiest way to find the magnetic field. So you can find the current enclosed, and you can find the magnetic field if your problem has symmetry. And of course, if you are given the curl of B or the magnetic field and the electric field, then you can also find the current density. By using the Ampere-Maxwell law. So this was a summary, a review of Maxwell's equations and how we've used them so far in our class. And I hope you will find this review helpful.